Today we're going to be talking about circular motion, which is pretty much just an object that is either rotating or revolving about an axis. Rotation is when an object is spinning on an axis that is within itself. For example, a top is a toy that a kid would spin, and its axis is inside it. The Earth spinning, which causes our day and night, is also an example of rotation. Another example is a skater that is twirling. Revolution is when an object turns or travels around another point, which is called the external axis. The Earth traveling around the sun is an example of revolution, and the sun is the external axis that the Earth is traveling around. Linear speed is distance that is moved per unit of time, and we know this from our kinematics unit. Tangential speed is another word that we use for linear speed when we are talking about the object's movement, the object's speed along a circular path. It is a straight line that an object would take if it flew off of the circle. For example, here, if we have an object that is going around in a circle, if it were to be let go or released, it would actually travel in this direction. If it was let go a little bit further down, then it would travel in a straight line wherever it was released. And it can be shown here that these are the directions that the object wants to go, but something is pulling it inwards that is keeping it on this trajectory of a circular motion. One thing to note is that speed does increase as the object's distance from the center increases. So as you go further away from the center, your speed will increase. And this is due to the amount of distance that you actually have to cover in order to get from point to point in this picture here. A tangent is a line that touches the edge of a point in a circular path. A tangent also plays a part in circular motion. This tangent forms a 90-degree angle to the radius of the circle. What you will notice, again, the object is continuously moving in a circular motion, therefore the tangent is always changing. As the object moves around, the radius will always be perpendicular to the tangent. And this is just showing you the direction that the object is traveling due to inertia. So circular motion is where an object is moving at a steady speed around the circumference of a circle of constant radius. Let's discuss what circumference is. So here's a diagram of a circle. We have the circumference being the entire perimeter of this circle. And what we know is that pi is defined as the circumference of a circle divided by its diameter. A diameter is equal to twice the radius, which is simply saying 2r. Rearranging this equation to solve for c gives us the equation for the distance that is covered by an object in one complete revolution. Capital C equals 2 pi r, and c is the circumference and r is the radius of a circle. The time the object takes to go around one full revolution or one full cycle, we call this period, and it is denoted by a capital T. The equation that we have in order to solve for speed comes from our linear speed equation, which is speed or velocity equals distance divided by time. And because we know that the distance is equivalent to 2 pi r for a circle, we then get 2 pi r divided by t for the speed of an object that is going around in a circle. Here's an example for you to try. A car drives at a steady speed of 8.4 meters per second around a roundabout. The car completes a single revolution in 9.0 seconds. Calculate the radius of the path taken by the car. Pause the video and start it back up when you're ready to check your answer. Okay, so what we know is the speed as being 8.4 meters per second, and we are given the period, or the time that it takes to do that revolution, is 9.0 seconds. What we don't know, and we want to know, is the radius. The equation that we will use is 2 pi r divided by t. When we substitute everything in, we get 8.4 equals 2 pi r divided by 9, and when we solve further for radius, we get an answer of 12 meters, which is to two significant figures. Frequency is another term that we use when we're discussing circular motion. And frequency is simply the number of times an object goes around a circle in some period of time, usually in 1 second. This is measured in hertz, Hz, or sometimes denoted as megahertz, because our answers can be in such large quantity that using megahertz allows us to use smaller numbers. And that is 10 to the 6th power, or sometimes even gigahertz. When we're calculating frequency, all you have to do is to take the number of revolutions, n, and divide it by the time of the total revolutions. When you divide this would give you hertz, which you can then change into megahertz or gigahertz. There is a relationship between frequency and period, and that relationship is that frequency and period are inversely proportional. If you look over here, we have period equaling 1 divided by f, and f is also equal to 1 divided by t. And so when you're solving for either of these two variables, they are always inversely proportional to each other. Here is an example for you to try. The rev counter on a car shows that when the car is sitting at traffic lights, the engine has an idling or resting speed of 840 revolutions per minute, RPM. Calculate the frequency of rotation of the engine and the time taken to complete a single revolution. Go ahead and pause the video and start it back up when you're ready to check your answer. Let's solve for frequency first. So what we know is that the RPMs are 840. We have 1 minute or 60 seconds. So notice that we are going to have to convert that minute into seconds. And what we don't know, but we want to know, is the frequency. The equation that we're going to use is F equals revolutions divided by T. When we substitute, we get F equals 840 divided by 60. And when we solve for F, we get 14 hertz. To solve for time, we calculated the frequency to be 14 hertz, and what we want to know is the period. Using the equation for the relationship between frequency and period, we have T equals 1 divided by F, and when we substitute our information and solve for period, we get a period of 0.071 seconds. Now, centripetal force, when we're talking about circular motion, everyone always thinks of this. So centripetal force, what is it? It is a force that's directed to a fixed center. It causes an object to follow a circular path. And remember, it always creates that right angle with the radius. It means toward the center, or center seeking. If you look in this picture right down here, you'll see the radius here. This is the direction of the force, so it pulls the object into the center. You're going to notice that the velocity can have constant speed, but the direction is always changing. So let's take a look over here, and you notice that there's an object that's traveling, and its inertia is going to want it to keep going in a straight direction, but it gets pulled for some reason, either by gravity or tension or electrical forces. And if they did not exist, then this object would just fly off at any of these directions, depending on where it is when the force is no longer there. So because we know that acceleration happens when there is either a change in speed or a change in direction, velocity can be constant speed, but because that the direction is always changing, we are experiencing constant acceleration. The object is always accelerating. Without the force, the object would move in a straight line, and the net force is pretty much the total, the sum of all the forces, right? And the reason why we have an object moving around another object in a centripetal motion is because the net force is stronger inward. So there's more force that's going inward, which is keeping the object in its circular motion. An example is where gravity is holding a celestial body, right? So it's holding the moon in orbit around the Earth. So here we have the moon, and it wants to go in this direction, but it's getting yanked in by the gravity of the Earth. So therefore, it's in an orbit, okay? And we call this gravity. This is causing the centripetal force. If the Earth were to disappear, it would just go whoosh, and it would just fly off into space in whatever direction it thinks it's going. So inertia says it's going this way. If the Earth disappeared when the moon was traveling in this direction, then the moon would just go right off the page over here in this direction. If the moon was over here, it would go this way to the right. So as you can see, it just it's very theoretical, of course, but if the Earth were to disappear, then the moon would just continue going whichever direction it wants to go, which is what inertia is. Another example is electrical forces holding the electrons in an orbit around the nucleus. So an atom has protons and electrons, and that protons are in the center and they have a positive charge. Electrons are on the outside and they're zipping all over the place, right? The only thing that's keeping the electron from just zipping off into nowhere is that there is an attractive force, which we're calling here, it has a centripetal force, and it also has something else that we have not yet touched on, which is centrifugal force. And so therefore, this inward pull, this attraction, is keeping the electron orbiting around the atom's nucleus. Now, in order to calculate centripetal force, all you need to know is that it is mass times speed squared divided by the radius of the curvature. And what that looks like is F sub c, c for centripetal, F for force, equals mass, which is in kilograms, and then velocity, or the speed, squared, which is meters per second, with all over radius of the curvature, which is in meters. And we get that from looking at what the radius or the diameter is. When you figure all this out, you would get your answer in newtons. And remember that a newton is just a kilogram per meter per second squared. Let's do an example. So a ball is moving at 12.6 meters per second on a 1.0 meter string. So you're twirling the ball around on the string. How much force do you need if you were to make a 10 kilogram cannonball move in the same circle at the same speed? So you're going to have the same radius, you're going to have the same speed, but now you have a different mass. So all you need to do, here's our picture of showing a ball that is going in this direction here and getting swirled around. Okay, so what you have here is F sub c, so this is centripetal force, equals mv squared over r. Plug everything in. This is your 10 kilograms. Your speed is 12.6 meters per second squared, all over the radius, which is 1.0, and you should get an answer of 1,590 newtons, which pretty much means you need about 1,590 newtons or 357 pounds of force in order to make a cannonball move in the same circle at the same speed. So it's going to take a lot more force to move a cannonball at the same speed as you are the smaller ball. Here's another example. What is the centripetal force acting on a 100 kilogram person if he spun around in an 8-meter circle at a speed of 10 meters per second? Try to calculate this answer before you start the video again. So you have the centripetal force equals mv squared over r. Your answer should be 1,250 newtons. All right, so the last thing that we need to talk about is centrifugal force. It is an outward force. It's that force that makes you feel like you're being pulled away from the center. It means center fleeing. It is the force that causes circular motion, but it is not a real force. Here we are with a person who is twirling something around him. Okay, so this object is feeling the tension, which is called the centripetal force, and it's also feeling the centrifugal force where the object is being pulled outward, as well as trying to be on its path of inertia. Okay, so that's all of our information. Be ready to use this and review the video again if anything is confusing.